In this video, I want to step through every assembly instruction in a program to observe the operation of the registers and how data moves to and from memory. I also want to show how functions work in assembly by tracing through a simple function call and return. To that end, I've written a C program with a simple main that calls one other function. We can compile that program to IA32 assembly using the -M32 flag in GCC. These other flags are instructing GCC to leave out some types of assembly instructions that are useful in practice but make the assembly code harder to read. And now that we've compiled to an executable called add, we can run gdb on our executable. Note that because we didn't compile with the -g flag, the debugger is unable to associate any C code with the executable, but we can still step through the assembly instructions in the executable and observe their operation. We'll put a breakpoint on the first assembly instruction of main, and then run. And now we can use the command that's short for disassemble to observe the assembly code near the point where we have paused execution. So this is the IA32 assembly that the compiler produced when it compiled our add2.c program. And the debugger is currently paused on the first assembly instruction of the main function. We can use the info registers command to see all of the IA32 registers and their current values. But since our program was so simple, most of these registers aren't going to be used, so let's take a look at the assembly code and see which registers it actually makes sense to pay attention to. Over the course of the program, we're definitely going to be changing the addresses in the base pointer and stack pointer registers. And we also see that data is being moved into and out of the EAX register. Also, we know that there are jump and call instructions, both of which affect the instruction pointer register. And so we can follow the values in those four registers to keep track of what's going on in the CPU. We'll use the Gdb Command Display, which causes a value to be printed every time the debugger pauses. So if we display EAX and the other registers, then every step that the program takes where we pause the debugger, we will see the values in all of those registers. We can use NI for next instruction to execute one assembly instruction, and then if we do disassemble again, we see that we're now on the second line of the assembly code, and now the instruction pointer is holding the address that ends in 505, which is main +1, and so that means the next instruction we are going to execute is this move instruction. The instruction that we just executed pushed the base pointer, and the push instruction puts a value on top of the stack. When we put a value on top of the stack, that moves the stack pointer up by one location, meaning by 4 addresses, since we're operating in IA32. And so, from the value of the stack pointer before that instruction, which ended in 47C, we now have a value of the stack pointer after that instruction that ends with 478, because we subtracted 4 to move the stack pointer up by one location, and that is the place where the data got put on top of the stack. And so the value that was in the base pointer register got pushed onto the top of the stack, and if we were to examine this memory location, we should see the value 0. We can do that with the X command in the debugger, and we can examine a memory location, and it has the value 0. This next instruction will move the value in the stack pointer register into the base pointer register, so if we execute that instruction, we now see the same value got copied into the base pointer. And the following instruction is subtracting 10 in hex, so 16, from the value of the stack pointer register and storing that value back into the stack pointer. If we execute that instruction, now the stack pointer ends in 468, and so that means that we moved the stack pointer up by 16 addresses, creating room for 4 32-bit values between the base pointer and the stack pointer that can be used for the local variables of the main function. Note also that for each instruction that we have executed, the instruction pointer has advanced to always be pointing to the next instruction we are going to execute. If we disassemble now, we are currently paused before executing this move instruction at main +6, and so the value in the instruction pointer register is the address in the code segment of memory where the next instruction of the program is stored. This next instruction is moving a constant into a location above the base pointer, so we are storing a value in one of the local variables. And if we now examine the location where we just put data, we see the value was stored at that location. And using our knowledge of hexadecimal and 2's complement, we can recognize that these F's are a bunch of leading ones, and then D means that we ended with 1101, and that is the 32-bit 2's complement representation of -3. And so from this we can conclude that the compiler chose to locate the variable I in memory at an offset of 8 above the base pointer for main. The next instruction, putting the value 0 at 4 above the base pointer, corresponds to initializing j to 0 in the C code. Now our instruction pointer has this address ending in 518, so the next instruction we will execute will be this jump instruction, and a jump instruction updates the value in the instruction pointer register. So when we execute this unconditional jump, our next instruction will be main +36, because the jump instruction is putting this value into the instruction pointer register. So main +36 is this move instruction, and so after main +20, the next instruction we execute will be the move instruction on main +36. This instruction loads a value from memory into the EAX register, and we know that that memory location is where the compiler decided to store the variable I. So we are bringing the variable I into the EAX register, and after we execute that instruction, we see the value -3 in EAX. In the next instruction, we are comparing a value retrieved from memory against the value in the EAX register. That location in memory is where we stored the variable j. So we are comparing the variables I and j, and then we are jumping if I is less than j. We know that the value of j is 0 and the value of I is -3, so we should expect this jump less to trigger, and that will jump us to main +22 by moving this memory address into the instruction pointer register. So if we execute the compare and jump, we should then find ourselves paused on this push instruction. The instruction pointer now stores this address ending in 51A, so the next instruction we execute will be this push, and we know that a push instruction puts data on top of the stack. The thing that we are putting on top of the stack is retrieved from the memory location where we stored I. So we are pushing the value of I on top of the stack. when we pushed, we subtracted 4 from the stack pointer. Its old value ended in 468, now it ends in 464, and at that memory location, we should find the same value that was in the variable I. And the reason that we pushed this onto the stack is that when we're calling the add2 function, we are passing the value of I as an argument to that function. So in IA32, before a call instruction that jumps into the code for executing a function, we first have to push all of the arguments to that function on top of the stack. That means that when we then set up the stack frame for the function call, just below the base pointer for that function, we will have all of the arguments that were passed into the function. This call instruction, as we see on the cheat sheet, does two things. It pushes the value of the instruction pointer onto the stack, and then it jumps to the label, and the label that we are jumping to is the label for the add2 function, where add2 begins at this location in the code segment of memory. So note that the current value of the instruction pointer ends in 51D. When we execute this call, just like in your Homework 4 CPU, the first step of executing any instruction is to fetch it, and then to increment the program counter. In this case, that will mean that the instruction pointer, when we have started executing the call instruction, will have just been incremented to now store this value that ends in 522. And so, when we push the instruction pointer on top of the stack, the value that we will be pushing will be this one, the location of the next instruction of main immediately after the call. That means that when we return from the function call, we will have on top of the stack the place that we want to return to, and so we can pop that off of the stack to tell us where do we resume executing when we come back to main. After pushing the instruction pointer, we have a jump, and that means that we will overwrite the value in the instruction pointer register with the location where the function starts, so that the next instruction we execute will be the first one in the body of the function. I used the ni debugger command. Next, we'll skip over function calls, as opposed to the step instruction, which would have gone into the function call. So we have just come back from the call to this function, and that means that we are on line 30 of main, right after the return from the add2 function. When we get back from this function, we see that in the EAX register is the value -1. And -1 is what add2 should have returned when called on the input 3. And so this shows us that in IA32, whenever a function returns, it always puts its return value into the EAX register. And so now, when we come back from the function call, the first thing that we are doing is moving the stack pointer back down to take the function input that we put onto the stack back off of the stack. And then, immediately afterwards, we are moving the value in the EAX register into the memory location for the variable I. So this is because in our C code we had I equals the return value from the function, and so the return value comes back to us in the EAX register, and so we move that value into the memory location where we are storing I. So we've moved the stack pointer back down, and if we examine the memory location for I, we see that it's now storing the 32-bit 2's complement representation of -1. Of note, the value in the EAX register is also 32-bit binary, and so it is also a 2's complement representation of -1, but the debugger is smart enough to know that data in a general purpose register like EAX is probably an integer, and so it makes more sense to display it in decimal than display it in hex like it does for things that usually store memory addresses. And so now we are back to main plus 36, which is the location that we jumped to at the beginning of the while loop on our first time through. So this moving the value of I into the EAX register and then comparing it against the value of j is checking our loop condition. j still has the value 0, and I now has the value -1. So if we execute those two instructions, followed by a jump less than, we would expect that I is still less than j, and therefore we will jump back to the main plus 22 location of the beginning of our loop body. And indeed, we find ourselves back at the top of the loop body with our next instruction indicated by the instruction pointer as the push instruction that passes the argument I into the add2 function. So now we're passing that -1 that is stored in the memory location for I, and that is now being pushed on top of the stack. And so now, if we step into the function call with the SI command in the debugger, we find that our instruction pointer is now storing the memory location for the beginning of the add2 function. And if we run disassemble, we now see in the debugger the assembly code that makes up the add2 function. So when we arrive at the beginning of this function, note that the base pointer is still holding the memory location for the bottom of main's stack frame. And so to have the base pointer and stack pointer appropriately set up for the add2 function, we need to save the old base pointer so that we can put it back when we return, and then we need to update the base pointer and stack pointer to point to the bottom and top of the stack frame for this function. So we push the base pointer, saving it on top of the stack. Then we are moving the value in the stack pointer register into the base pointer register. So first we push, which increments the stack pointer by 1. Then we move, which copies the value from the stack pointer into the base pointer. So that has the effect of moving the base pointer up to point to the place where the stack pointer currently is, and then immediately after we are subtracting from the stack pointer, which moves it up and creates room for the local variables of the add2 function. So these first three instructions of the assembly code for the add2 function look an awful lot like the first three instructions of the assembly code for main. And that's because whenever we call a function, the compiler needs to move the stack pointer and base pointer to give room for the local variables of the current function. And in fact, the normal operation of the debugger when you give it a breakpoint based on your C code is that it will skip over the first three assembly instructions of any function call because those correspond to setting up the stack frame, which is part of calling the function, and doesn't correspond to code in the body of the function that you wrote in C. And so now we have arrived at the first instruction that corresponds directly to C code in the function, which is that we are moving the value 2 into a memory location just above the base pointer. So this is assigning the value 2 into a variable in our C program. And then we are moving a value that is below the base pointer into the EDX register. So before this instruction, we can print the value in the EDX register, and it happens to be holding -3. But when we execute that instruction, now we have moved the value -1 into EDX. Why was this a location with -1? Well, that's because before we made the function call, we pushed the argument to the function, which was -1, onto the stack. We then pushed the instruction pointer and the base pointer as part of calling the function, and so now the new base pointer is 2 memory locations above the place where we pushed the function argument. And so 8 below the base pointer is where we put the argument that we were passing in to the add2 function. So here we are loading that value into the EDX register, and then we are moving this value that we stored in our local variable into the EAX register, and then we are adding those 2 values with the result ending up in the EAX register. So we will be adding 2 plus -1 and putting the result in the EAX register. If we execute those 2 instructions, we see that now the EAX register has the value 1, and we're about to return from the function. And so before returning from the function, IA32 puts the return value in EAX, so on this call to add 2, we are returning the value 1. Now we get to the leave and ret instructions, which are also outlined in our cheat sheet. The leave instruction does 2 things. It moves the base pointer into the stack pointer. So that means that we're going to take the value stored in the base pointer register and copy it into the stack pointer register, which means that the stack pointer is being brought to point to the same place as the base pointer. So we are collapsing the stack frame for the add2 function in preparation for returning back to the main function. Then we are popping into the base pointer register. So when we pop, that moves the stack pointer down by 1 and puts the value that was on top of the stack into the destination register. So we will take a value off of the stack, moving the stack pointer down, and put that value into the base pointer register. But remember, we saved the base pointer register on top of the stack back at the start of the function. And so now when we pop back into the base pointer register, we are restoring the base pointer for the bottom of main. So executing this leave instruction initially brought the stack pointer to 45C, the same place as the base pointer, but then when we popped, we brought it down by 1 more to 460. And when we popped, we restored 478 back into the base pointer, which was, from before our function call, the location of the base pointer for main. Now our instruction pointer is storing the address ending in 503, which is the ret instruction, and so we are about to execute ret. And referring to our cheat sheet, we see that this has the result of moving a value from memory into the instruction pointer, and then we are adding 4 to the stack pointer. So moving the value from the stack pointer and then lowering the stack pointer is equivalent to doing a pop. So what we are doing is we are popping something off of the top of the stack and putting that into the instruction pointer register. But recall that when we did the call in main, part of that instruction was to push the instruction pointer onto the stack, so we were saving the location in main that we wanted to return to when we came back from the function. And so now we are restoring into the instruction pointer register the value that we saved before we called the add2 function. And so now that the instruction pointer is updated to have that same next instruction that it had before the call, we will next execute the instruction immediately following the call instruction in main. So now our instruction pointer has been updated to this address ending in 522, and so the next instruction that we will execute is this add instruction, that is lowering the stack pointer one more time to throw out the argument to the add2 function. So now we have restored our base pointer and our stack pointer for main, and our instruction pointer is on this move instruction that will store the return value from the function. And if we were to now examine our memory location for I, we see that it stores the 32-bit 2's complement representation of the number 1. And so, when we load that into the EAX register and compare it to J, whose value we know is 0, we expect that this jump less than will no longer trigger, because the value in EAX should be 1, and the value of J should be 0, so this is not less than this, so our jump less than will not trigger, and so rather than jumping back to main plus 22, we will simply continue on to the next instruction, which is this move instruction. And moving the value 0 into the EAX register before leave and ret corresponds to returning the value 0 from our main function, after which we will execute leave and ret and conclude the program. That was an awful lot to keep track of, so we should draw ourselves a diagram of the registers and memory that's being modified over the course of executing this program. Let's step through our add2 program and trace through all of the assembly instructions and their effects on the registers and the stack region of memory. On the board, I've represented the relevant CPU registers that we saw changing in our execution of the program, as well as the relevant regions of memory. Note that both the code of the program and the data on the stack are stored in RAM. So all of these addresses in the program that start with 565 are referring to memory locations within the code segment, and at those memory locations are stored the binary representations of various assembly instructions. This would be the output of the assembler, which is the executable that we are running, which has been loaded into RAM so that we can execute it. On the other hand, the addresses that start with FFF all correspond to locations on the function stack, and so these are where the local variables for the main function and the add2 function get stored. When our program arrives at the start of main, we have the instruction pointer storing the address of the first instruction of the main function. And our stack pointer is storing a very large 32-bit value, and so this stack segment of memory is near the end of the program's address space. For many of the registers and memory locations, we don't know what they're currently storing. We could, in principle, inspect these locations using the debugger, but the data that's there is just garbage left over from whatever the computer was doing previously. So we'll indicate that with question marks for the values that have not yet been assigned during the execution of our add2 program. The first 3 assembly instructions of main we know are setting up the stack frame for the main function. We are first pushing the value in the base pointer register, which would allow us to return from the main function, but the base pointer before we've even started executing main just has the value 0. When we execute a push instruction, we are putting something on top of the stack. So if the current top of the stack is here, then we need to move the stack pointer up by 1 and put the data at the new top of stack location. So moving the stack pointer up by 1 corresponds to adding 4 to the value that is stored in the stack pointer register, so that it is now storing this address that ends in 478. And then we are putting the data from the source register into that location in memory. And so the 32-bit 0 that is being stored in the base pointer register is getting placed in this memory location. We could just write this as the number 0, but I'm going to stick to using hex values with 8 hex digits for all of the memory addresses and numerical values for the general purpose registers. So, since the base pointer generally stores an address, I'm going to treat this as an address. But we've neglected a change that happens on every instruction, which is that the first part of any instruction is fetching and incrementing the program counter. So the instruction pointer register should have gotten incremented to point to the next instruction before we began executing this instruction. Now that we've completed the push instruction, we are next performing this move operation. Again, the first thing that happens is always that we fetch that instruction from memory and update the instruction pointer. So the instruction pointer will be updated to point to the next instruction, which is 507. And now we are actually performing this move. So this is copying a value from the stack pointer register to the base pointer register. So we are copying this value into the base pointer. And so that means that right now the base pointer is pointing to the same location that the stack pointer is pointing. But on the very next instruction, we are going to move the stack pointer by subtracting 16 from it. So here we fetch the instruction, increment the program counter, so it will now store 50A. And now we are executing this subtract instruction, which is subtracting 10 from the value in the stack pointer register and storing the result back into the stack pointer register. So when we subtract the hex value 10, that's the decimal value 16, but that changes this hex address to be 468. And so that means that we are moving the stack pointer up to here, which gives us room for the local variables in the main function. Next, we're executing a move instruction. This was initializing the variable I. We'll increment the program counter. And then we'll put this value into the memory location that is base pointer -8. In RAM, every byte of data, that's every 8 bits, corresponds to an address. But since we're working with 32-bit values here in IA32, we are operating with 4 bytes at a time. And so we are going 2 4-byte values above the base pointer to store our value -3 for the variable I. Now we fetch this move instruction and increment the instruction pointer. And the move instruction is copying the value 0 into base pointer -4, which is this location in memory. And that's our initializing the variable j. The next instruction is a jump. We will start, as always, by fetching the instruction and incrementing the program counter. So we get 51A in the EIP register. But then, when we jump, we are immediately overwriting the instruction pointer with the address that was stored in the jump instruction. So this gets copied into here, and so we have 528, meaning that our instruction pointer, rather than just incrementing by 1, has now jumped down to here. For this instruction, we fetch and increment. And now we're executing the move instruction that is bringing the value from base pointer -8 into the EAX register. I've mixed up the values in the base pointer and stack pointer registers. I changed the base pointer earlier when I should have changed the stack pointer. So this is 6, 8, and this is 7, 8. So when we subtract 8 from the base pointer, we get 7, 0, and so that's this memory location. So we are loading data from this memory location into the EAX register. The next instruction will compare the value in this memory location to the value in the EAX register. We'll start by incrementing the instruction pointer. And base pointer minus 4 is 474. So we bring in the 0, and we are comparing 0 versus minus 3. The result of this compare operation is being stored in the flags register. And so then the next operation, the jump less than, will be checking the values in the flags register to see whether or not we should jump. But for our purposes, it doesn't really make sense to reason about the specific values in the flags register, because we can understand the semantics as we are comparing these two values and then jumping if B is less than A. So now executing this JL instruction, we first increment the program counter. So the program counter now stores 530. And then if this is less than this, we will overwrite the program counter with the destination of the jump. Since, in fact, B is less than A, we will jump, and so we will load 51A into the instruction pointer, which jumps us up to this as the next instruction we will execute. On this instruction, we fetch and increment the instruction pointer. And then we are pushing the value retrieved from base pointer minus 8. So the base pointer has 478, subtracting 8 gives us 470. So we are retrieving data from this memory location, and we are pushing that minus 3. When we push, we move the stack pointer up and put the data on the new top of stack location. So the minus 3 will end up here, and we are moving the stack pointer up by 1 location. And that means that the stack pointer register's value is being updated. We are subtracting 4, which moves us by 1 4-byte value. Now we're on the call instruction. We'll fetch and increment. So instruction pointer becomes 522. And this is the one place where it really matters to keep track of the instruction pointer as we go. Because by storing the value of the instruction pointer now, we will know when we eventually return from the add2 function, where in main are we coming back to. So the call instruction will push the instruction pointer. So push means we're moving the stack pointer up by subtracting 4. And then at that new location, we are putting the value that was pushed. And since we were pushing the instruction pointer, we are saving this 522 address of the next instruction after the call. Then the call jumps us to the memory location given here. So we put this into the instruction pointer. So that becomes 4ED, meaning that the next instruction we will execute is this one. At this point, I think you get the idea of the incrementing of the instruction pointer at the start of every instruction. So I'm going to stop keeping precise track of it, and we'll just think about what its value should be in the cases where it's going to make a difference. Now at the start of our function, we push the base pointer register because we want to know where do we restore the base pointer to when we return from this function. So this value gets stored on top of the stack, and the stack pointer moves up. Now we execute the move instruction, which copies the value from the stack pointer register into the base pointer register, which brings our base pointer up to here. And then we subtract 16, 10 in hex, from the stack pointer, which moves the stack pointer up to here, making room for the local variables of the add2 function. Now this move operation, corresponding to initializing a local variable in the function, is storing the value 2 at base pointer minus 4. So the base pointer stores 45C, so subtracting 4 gives us 458, and so at this location, we are storing the number 2. Then we are retrieving a value from base pointer plus 8. So the base pointer is 45C. If we add 8 to that, we get 464. So that means we are retrieving a value from here and bringing it into the EDX register. Now we are copying that local variable that we saved in the stack frame into the EAX register. So base pointer minus 4 is this location, so we are loading the 2 into EAX. And now we are performing an add operation where we are adding EDX and EAX, and since EAX is the second argument, that's the destination, so the sum will end up in the EAX register, so we get a -1 here. And since this is immediately before leave and ret, we know that -1 is the value that this function call is returning. At this point, our instruction pointer is on the leave instruction. So when we fetch that and increment the instruction pointer, this becomes 503. Then we execute the leave instruction, which does two things. It first moves the value from the base pointer register into the stack pointer register. So that's bringing the stack pointer down to the same position as the base pointer, which collapses the stack frame for the function that's about to return. And then it pops into the base pointer register. A pop will move the stack pointer down by 1. So this becomes 460. And then the value that we just took off of the stack goes into the destination register, which in the case of a leave is always the base pointer. So into the base pointer, we store 478, which corresponds to bringing the base pointer back down to the bottom of the stack frame for main. Now we execute the ret instruction. So we first increment the instruction pointer, but we're about to overwrite it because we will, on a ret instruction, pop into the instruction pointer register. So this value here was the old instruction pointer that we saved when we called this function, and so now we are restoring that back so that the next instruction we execute after we return will be the position right after where we called the function in main. So the pop will lower the stack pointer, and the value that we just took off the stack, in this case, goes into the instruction pointer, meaning our next instruction will be this add instruction that immediately followed the call. Now back in main, we will proceed with these instructions, and I will again pause on updating the instruction pointer every time. So now we'll add 4 to the stack pointer, which is like popping the -3 off of the stack, but that was an argument to a function that is done, and so we don't need to put that value anywhere. So rather than popping it into a register, we just move the stack pointer down to say that's no longer in the stack frame. Now we move the return value into the location where we stored our variable I. So we're taking the value that's in the EAX register and putting it at the base pointer -8, which is 470. So we are overwriting this memory location with the -1 from EAX. Next, we move that value that we just stored back into the EAX register. So this move didn't change anything. And then here we are comparing 0 against -1. And we will jump if -1 is less than 0. So we do, meaning we jump up to 51A, where we are about to call the function again. This time when we call the function, we are again pushing base pointer -8. So base pointer is still here. Base pointer -8 is still this memory location, but we've updated that value. So this time we are pushing a -1. That moved the stack pointer up, and we also incremented the instruction pointer. And so then when we get to this call instruction, the fetch and increment will put the instruction pointer here, storing this 522. And so when we call the function, we will again push the return address onto the stack. It turns out in this case, since we are calling the same function from the same place in main with not much having happened in the interim, that we're actually just pushing the same value that is probably still there in memory. And so now we'll execute the function again. And so the function will, as it executes, load this -1 into the EDX register. And then it will load the 2 into EAX. And then it will perform the addition, storing the result in EAX. And so then when we leave and ret from the function, we will end up back at this location with EAX, the return value of the function, being 1. And so when we add 4 to the stack pointer, it will come back down. And then we move this value into 470. And so now we have a value 1 here, which again we copy back into the EAX register, and we compare it against the base pointer -4. Let's get everything up to date for this point. So we are executing this compare instruction, and then we're going to do the jump less. So on the jump less, when we fetch this jump less instruction and increment the instruction pointer will now be storing 530. And since the compare operation we just did was this time with a +1, because we were comparing the value in the EAX register as this argument, and the value from base pointer -4, the 0, as this argument. So the comparison and jump less, B is not less than A, and so this time we will not jump. And so rather than putting this destination into the instruction pointer register, we simply go on to the next instruction. And so we will fetch whatever the instruction pointer is pointing to, which is this move instruction. When we fetch, we also increment the instruction pointer. And then we execute the move instruction, putting a 0 into the EAX register, corresponding to returning 0 from the main function. Then leave and ret will operate as we saw, but when we return from main, there's nowhere to go and our program is done. So now we've seen in full how the base pointer and stack pointer registers move when we make a function call to keep track of the portion of memory that is being used for the local variables of the current function. And because all of our references to local variables in our functions compiled into offsets from the base pointer, wherever the base pointer and stack pointer end up pointing, we'll know how to find the local variables of our function. And we also saw that when we call a function, we have to save on top of the stack the instruction pointer for the place that we're going to go back to when we return, and the stack pointer that we are going to restore to the calling function when we're done with the stack frame for the callee. So now you know how to trace through assembly code in the debugger and how function calls work in IA32.